So, who's working with Node in here? Good, good. Right crowd then. Okay, who's ever had a production issue with Node? All right. Okay. Cool. So there's those that have, and there's those that are going to. So my name's Dave Clements. I'm with Nearform. Found out today that we actually sponsor this, so you're welcome. So yeah, we, as pretty much everyone else in here likes to say, we are hiring. We're looking for Node developers. A lot of people in here doing Node. Both for remote work and work here in London, and if you fancy, there's work in New York for you too. So, come talk to me or Sean if you like tall, dark, and Irish. Okay, so speaking of production issues, some people put their hands up. They felt this pressure. They felt this situation. You get to a point sometimes where some kind of production incident happens, or something's deployed, and things start to lock down. When the sales traffic drops, people get angry. So, what do you do in this situation? Anyone? I know you're not supposed to ask questions, but you can answer my questions. What would you do in a case where things were just going so slow that production, like your sales traffic's dropping? Quick fix. You're on the spot. Guys, you're all losing money right now.
Turn on and off.
Turn it on and off. Perfect. Yeah, perfect London response. I did this in New York and I got classic New York sarcastic responses, and then this is like a different version of that for London. You add more servers, right? You add more instances. You have to scale up very quickly, and you need to do it now. If you're using a cloud deploy, you're going to use that elastic scaling quality to solve the problem quickly. But now the business is spending more money, and we need to ask the question, why is it slow? So the answer to that question is another question, which is, where is the bottleneck? And when we ask the question, where is the bottleneck, we want to figure out, is the bottleneck internal to a process, or is it external? Is it somewhere else in the infrastructure? So I think the reason there was a lot of silence around what do you do in this production situation is because a lot of people, when they're working on Node, are working in a layer within a stack. And there's other people responsible for keeping things running and spinning up more servers, right? But what can happen is sometimes your team or your project that sits in the middle here, when someone's asking why is it slow, someone will be asking, is Node slow? Is your project slow? And then you have to try to figure out and prove, is the bottleneck in this entire system in my application, or is it external to my application? And bonus points, if it is external, can I figure out where in the stack it is? So how do you find a bottleneck? Because if you can find a bottleneck, you can prove whether the bottleneck's in your application or some upstream API, etc. So first thing is you have a performance issue. And something happens in production, maybe the servers don't crash, but maybe there's some diagnostics come back from, I don't know, maybe you got New Relic in there, or from health checks, whatever it is. You get some diagnostics, but they're coarse-grained, they're polluted, very hard to figure out what's going on in that situation. So the next thing that you typically would do is you try to reproduce this on a production-like environment, a kind of staging environment that you can play with, that you can run traffic through, that you can simulate load on. And to simulate load, first tool I'm going to be introducing is autocannon. So autocannon, has anyone heard of Apache Bench before? Yeah, cool. There's another one called WRK2, you heard of that? No? Okay, so these are HTTP load testers, both written in C. Both quite difficult to set up, especially on Windows. Autocannon's written in Node. It can actually saturate your server 10% more than Apache Bench and WRK. And it's as I say, just written in Node. So you can just npm install Autocannon. It'll work on Windows and everything. So it's actually brought into the Node core project as a load testing tool because it's so easy to get it working on Windows as well. So you would have maybe a staging environment, and then you could simulate load with Apache Bench or Autocannon or something like that. But your diagnostics are still fairly coarse-grained. You're really just getting requests per second averages and so forth back. So the next thing you do once you've tried to diagnose the situation in production and maybe honed in on an area in the system is you reproduce on development box. It's not a live environment. You're trying to isolate the scenario. In your case, if you're doing this on your development box, it's going to be a Node process if you're working with Node. And then you want to have fine-grained diagnostics where you're going to use special flags like trace opt, trace deopt, tracing lining, stuff like that to try to figure out possibly where in the process you might have a bottleneck, and then this is actually the way that myself and my colleague Matteo Collina work is we just stare at the screen for a really long time trying to figure out what's going on. You've probably been there, right? And Matteo, who made the original version of this, he has a dog. He's an Italian. He's got curly hair, brown eyes, and he's got a dog called Pufetta. And there's some Italians in the room. They probably know that Smurfette and he's got brown eyes and curly hair, and basically looks like his child. But he'll take her for a walk, and then he'll have epiphanies. Me, I like to take long showers. There you go, mental image. And then some magic happens in our animal brains at that point, and we get to perform an application. However, what we want to do is, Nearform, what we've been working on is optimizing that magical question mark step and trying to make that, take the pattern matching that we're really doing in our minds when we're trying to figure out where the bottleneck is and where the problem is, and turn that into tooling and visualizations that surface those patterns faster and make it much easier to prove where the bottleneck is. So Node Clinic's installable with npm. You can just do -g clinic, whole thing installs, and this will give you 3 tools. The 3 tools are Clinic Doctor, Clinic Bubbleprof, and Clinic Flame. Clinic Doctor, what it does, it's your GP for a node process. It will collect metrics by injecting probes, and then it assesses health with a set of heuristics that we developed with a statistician. Yes. I've had problems with that word in the past. Who's basically using statistics algorithms to map the pattern matching I was talking about that we do with our brains into an algorithm that can automatically detect issues with a node process and categorize them for you. And then from that, Clinic Doctor creates recommendations. I'm going to live hack all of this in a second. Clinic Flame is based on a tool that I wrote called 0x, and this collects metrics by CPU sampling. And the thing that it tracks is something I refer to as top of stack frequency. So essentially, you're taking a millisecond slice of whatever the call stack is on the CPU at a given time. And that call stack can be translated to include not just the C functions that are on that stack, but also the JavaScript functions that are on that stack. Now, when you get into JavaScript land, if over successive samples, you have a higher ratio of a function being the function that's currently being executed, which means at the top of the stack, in higher ratio to other functions, then it's said to have a high top of stack frequency, and it's probably going to be a hot function, a function that's taking more time to execute because it's not calling other functions after it. And flame graphs visualize this by visualizing all of the stacks in aggregate, which you're going to see in a second, and coloring the top of stack blocks of frames with a high top of stack frequency, a deeper hue of from a spectrum of orange to red. So when you get red blocks, that's the pattern that you're looking for as a human. So you look at the graph and you see red blocks and you go, okay, there's where my bottlenecks are, which we'll see shortly as well. And finally, Clinic Bubbleprof is a tool that Nearform developed recently that introduces a new visualization for visualizing asynchronous activity. So whereas Clinic Flame is for identifying synchronous blocking functions within a process, a typical problem when you're working with Node, Clinic Bubbleprof works at visualizing I/O, waiting for I/O, and what's happening in that period of time. So this is useful for bottlenecks outside of your application rather than bottlenecks within your application. So Bubbleprof collects metrics using async hooks, which is a fairly new API. It's just about settled down in Node 10. It's not quite right, I don't think, but it's good enough that we can use it for development tools. The async hooks module will basically give you stats on every async action that happens in Node core as you're running a Node process, and also you can instrument other libraries. So for instance, MongoDB I think is instrumented with async hooks as well, so you know what asynchronous activity is occurring, and it can get better over time. So this creates bubble graphs. Okay, you can go to nf.ie/interact if you want to check out the actual visualizations I'm going to be creating. Okay, damn, I ruined it. You shouldn't have seen that yet. So I'm going to start our process, node 1. And I'm going to, first of all, the first thing I'm going to do is establish a baseline by putting it under load with the tool I mentioned earlier. So autocannon. I'm going to give it 2 connections because it's known to be problematic for 5 seconds. And I'm just going to hit it with HTTP correct, so 5 seconds, 2 connections. Okay, so right here we have an average request per second of 12 requests per second. Is that fast enough?
Depends what you're doing.
Yes, that's correct. It does depend on what you're doing. However, 12 requests per second is, we're getting kind of down the low end of like what could we possibly be doing that we would be, it depends on how much money you're willing to spend on extra servers. And yes, of course, it depends on what you're doing, but when you're getting down to that low of a number, maybe you should be using something other than Node if it's going to be very compute-heavy processing, because it's definitely going to do better on synchronous tasks. But is the bottleneck synchronous? Is it external or is it internal? Well, we can find out very quickly by using Node Doctor. So if I stop this guy up here, why didn't he stop the first time? I don't like it when it disobeys me. Okay, it's a weird thing to say. So what I'm doing here is I'm going to use Clinic Doctor, and I'm going to use a flag called onPort. What this allows is when the process that I'm about to run opens a port, it will trigger the command within that's assigned to the onPort flag. So what I'm doing here, this is actually 3 commands in one. So Clinic Doctor starts up. It instruments the process that I'm telling it to run, which is node 1. And then when that process opens its port, which is 3000, it will execute this command. So in one command, I can essentially find out what's going on in my process and if it has any issues. And this opens the Doctor display. So we've got CPU usage, memory usage, event loop delay, active handles. Active handles are like sockets that are open and so forth. And it says that it's got the CPU usage graph highlighted in red. And it says at the top, it's detected a potential I/O issue. The reason for that is that the CPU is idle too much of the time. Now this graph is a little bit misleading because we're seeing a lot of spikes. Those spikes are actually coming from the sampling. We've just released this. I'm not showing it right now because I didn't want to update, but we've just released a new version of Doctor that uses TensorFlow with a new algorithm written by a statistician that flattens this graph by applying an algorithm that sort of removes the extra noise. So when you install it, you probably will see a more flat CPU usage graph. But nevertheless, it has detected the I/O issue. Down here we have recommendations, and it will actually go into great detail on how you can handle it and mitigate it and different things. But the main point here is that to diagnose, it instructs to, say, use clinic Bubbleprof. Because it's an I/O issue, it means that something's happening outside the process rather than inside the process. So we want to see what's going on with the asynchronous activity using Bubbleprof. So what I can do is I can take that same command that I ran with Clinic Doctor and just replace Doctor with Bubble. Do the same thing. Put it under load for 5 seconds, 2 connections, and it creates this bad boy. So this is a little bit to consume visually, but essentially the bubbles represent the aggregated synchronous and asynchronous time that a particular group was seen operating, and the groups are based on the way the async hooks are used by a library or by Node core. So Fastify is a really fast web framework. That's why that's right at the top there. So Fastify is being used to serve. It's similar to Express or Happy. And then we see we've got a Mongo.js cursor over here, and we've got something else to do with Mongo.js over here. If I hover over this line, it says that 94% of the profile runtime, 4.9 seconds, async operations were pending from this group. It says a similar thing over here. So what I can do is I can click that line, and it breaks it into further 2 lines. I click the next one, and it gives me a stack trace, an asynchronous stack trace with the origin point of this particular asynchronous activity given to us. So it says 1JS line 11, column 7. So if I go to 1JS line 11, column 7, we see that what it's calling is find. So this is a MongoDB collection, and it's calling find. So that's going to start triggering some asynchronous activity. And what this is basically telling us is that it's spending a lot of time, 4.9 seconds out of 5 seconds in aggregate, waiting for that MongoDB response. So that tells us that the problem isn't in our process. The problem is somewhere, maybe with MongoDB. So why don't we take a look at, there's my Blue Peter earlier attempt. Why don't we take a look at the REPL and open the REPL and run that command. So I'm going to use it's basically this delivers the last piece of JSON in all of the NPM modules. So it's a big database. Modules is the collection, and then I can take the command that we're running here and run the same command in the REPL. And that gives us the response. Cool thing that Mongo gives you is the ability to do an explain. So it can tell you what that command is doing in Mongo. And if we look down here, it says that the plan is cold scan, which means that it's got to go through all of the keys in the database. Anyone who's worked with databases knows you need a index, thank you. So let's see if, oh shit, that's not how you do a clear in this. Let's see if there's any other collections available. Oh, check it out. So we have an index version of that collection. So the solution here may just be to index the database. So in 2JS, I'm going to go from DB collection modules to DB collections modules index. That's the only change. So back to the start. Run the second one. autocannon, localhost, 2 connections, 5 seconds, localhost 3000. Let's see what effect this has had, if any. Not a great one, but it's improved. It's improved. I think that usually when I do this, it goes from 2 requests per second to 100 requests per second. For some reason, that first time round was 12 requests per second. Ruining my talk, man. Not contrived enough. Okay, let's try it with a higher amount of connections. Oh, so a little bit better. Okay, so, okay, let's see. What I can do now is I'll run that same doctor command as before, higher amount of connections because clearly it can handle it, and see if, node 2, and also sockets, the port's open, that's why it's done that. So let's see if there's anything else wrong with the process now that we've fixed that problem. So now that we've solved the I/O issue, it's exposed another issue. In this case, it's the event loop delay. Does everyone, if everyone's working with Node and JavaScript, I assume you understand the event loop? Right, and blocking the event loop is a really bad thing, especially in Node, more so than in the browser unless you're doing like animation or gaming stuff in the browser. In Node, you tend to have one path that's used a lot, and you want it to handle a lot of connections. So if you're blocking, those connections pile up, and you end up in trouble. So this is now, because the I/O issue has been resolved, the actual work that the process needs to do gets done, but we're seeing that there's a synchronous bottleneck now. So the recommendation is run clinic flame. So same exact command, instead of doctor, flame. So what this gives us is a flame graph. And I'm going to press merge to make it even clearer. Merge takes frames that are the equivalent from a JavaScript perspective, but not from a C perspective, i.e. optimized frames and unoptimized frames, munges them together. So we can see that we've got stacks calling, functions calling functions. The width is how long it was seen on CPU, but the most important metric, which I mentioned earlier, is top of stack frequency. And the top of stack frequency here is very high, 71% on top of stack, and that's why that block is super red, and it's actually the same function over here. It has a suspicious name. It's named compute magic. Let's take a look at that. So compute magic is doing stuff that we really don't need to be doing, and sometimes you do find this in code that's deployed. There's just code in there that doesn't need to be there, and in this case we have a very easy solution. We just remove the code. If we removed all code, everything would be super fast. But we're going to just remove compute magic, and 3JS is just essentially the same thing, but with the call to compute magic and the compute magic function removed. See, it's sitting in the request path, slowing things down. So let's see how that's done. Oh, cool. 1,300 requests per second. Pretty good improvement from 12 requests per second. And we could run Doctor one more time just to see. Don't forget to close it. And Doctor's not found any other problems. There's probably more optimization you could do, but in terms of big walloping problems, this process is now doing what it should be doing. So it wasn't me is referring to the fact that I didn't do all of this work on my own. I did do the majority of 0x and wrote the recommendations for Bubble and so forth, but there is a team. Basically, there's a team of people behind this. Andreas Madsen, he's a Node Core contributor. He's a statistician I was talking about. Joy, she's a designer that created the logos and the different things. Connor, our product guy, Matteo Collino, I mentioned earlier. See what I mean? And then Matthias Booz is known as Macintosh Online, very smart programmer. Alan helped us with our front end stuff. Camille, who's here with me in London now, working on a project that we'd love to hire you for as well, and myself. Thanks everyone, appreciate it.